So, hello everyone, welcome to session 7B. We have 5 talks in this session, and the first talk is by Christian Wolf Nielsen on near optimal decremental SSP in dense weighted graphs.
Thank you. Thank you. And this is joint work with Aaron Bernstein and Maximilian Probst-Gutenberg. So the problem we're looking at is we're given an edge-weighted directed graph, G, undergoing an online sequence of edge deletions, and then we have a fixed source vertex R. And the problem is to obtain an efficient data structure that can maintain single source shortest path distances from this root R. So at any point in the sequence of updates, the data structure should be able to answer a query for such a distance in constant time. So there are two main settings, the exact and approximate setting, and our focus is on the approximate setting. And here the data structure is only required to return an estimate of such a distance, which should never be an underestimate and can be an overestimate by up to a factor 1 plus epsilon. So just to simplify my talk, I will only consider unweighted directed graphs. So let n be the number of vertices of the graph. Then our main result is that we can get roughly n squared total update time. And this will therefore be near optimal for dense graphs. So I should say that the previous best bounds were polynomially worse than n squared here. So the overall idea of our data structure is to make G like somehow similar to a directed acyclic graph, a DAG, and then use a data structure which is fast for such graphs. So let's, as a warm-up, just assume that G is in fact a DAG. Before I proceed, I'll just go quickly over a classical data structure, the even-Sherlock data structure, which maintains an exact single source shortest path tree T. And the idea is that when a tree edge is deleted, let's say this edge here, then for every vertex that got disconnected from the root, we'll scan its ingoing edges and look for a parent that keeps this vertex at the same distance. So in this case, distance 2 from R. And let's say that later on this tree edge was deleted and the scan proceeds and there's no edge that keeps W at distance 2. In that case, the estimates will be increased by 1 for W, and then this process repeats. So if T is only required to be maintained up to distance delta, then it's easy to see that the total amount of time you need is O of m times delta, because you only need to scan each edge at most delta times, so once per edge per distance increase. But we're not interested in exact distances, so let's do something more lazy. Suppose that W is only allowed to scan an ingoing edge at x, W when the distance estimate from R to W is divisible by some integer I. And this integer I can depend on this particular edge here. Then you can show that this gives an additive error in the distance of at most I minus 1 for any shortest path distance that contains this edge. But now on the plus side, we gain a speed up because now this edge only needs to be scanned order delta over I times instead of order delta times. So let's see how we can use that for DAGs. So in the rest of my talk, I will only focus on approximating distances in some range like this. You can just have a logarithmic number of data structures for each of the logarithmic many distance scales. So let tau be a topological ordering of the n vertices. And let's focus on one vertex W in the following. So we will apply this lazy ES structure from the previous slide, which only scans an edge XW satisfying these two inequalities if the estimate from R to W is divisible by this integer here. So this is our integer I from before. And here I'm looking at an edge such that the topological order difference between its endpoints is at least 2 to the j and less than 2 to the j plus 1. So as an example here, the topological order difference is 3. So you could pick j equal to 1 in this case here. Okay, so how many edges can there be that satisfy these two inequalities? So how many edges ending in W can there be? Well, there must be less than 2 to the j plus 1 such edges. And each of them is scanned no more than O of delta divided by our index I from before, so this number here, and this amounts to this many times. And now you see that this 2 to the j cancels out with this 2 to the j plus 1. And so if you sum over all W and over all possible j values, it's easy to show that now you get roughly n squared total update time. And the reason why we get 1 plus O of epsilon approximation factor is because we have this inequality here. So if you take any shortest path, in fact, any path at all, pi, and you sum over all the edges of this path of the topological order difference of the endpoints of this edge, then it's at most n. This is because it's a DAG. And this is really where we use the fact that the graph is a DAG. And then you can combine this with the fact I mentioned before about the additive error being at most I minus 1 on a previous slide to show that the total additive error is O of epsilon delta. And because our distances are in this range here, this will amount to this multiplicative error here. So let's see how we can generalize this to arbitrary graphs. So the first attempt would be to take any strongly connecting component and just contract it to a vertex. That will give you a DAG, and now we could apply this DAG structure from before. But of course, the problem is that, let's say the whole graph is an SCC, you'll just contract it down to one vertex and you will underestimate distances by way too much. So the second attempt is to only contract SCCs X for which the diameter of this SCC X is at most this value here. Okay, so how much can you underestimate distances now if you only contract such SCCs? Well, the total size of all SCCs is n, total number of vertices. So if you sum over all SCCs, the total amount you can underestimate is epsilon times delta, which is fine because now you can just add this value to your distance estimate and you will not get an underestimate. And you get a 1 plus O of epsilon approximation. But the problem now is we have some SCCs that we cannot contract. So how do we deal with them? So first, let me just describe something I will call a one-way separator. So let's look at an SCC X and pick some starting vertex S and grow a BFS tree from that, from S. Now pick any BFS layer, let's call that ESEP, so these blue edges here. If you remove these blue edges, then there cannot be any edge going from the right-hand side to the left-hand side over here, because it's a BFS tree. So that's why I mean by a one-way separator, there cannot be edges of this type here, these red edges here. So now the idea is to do the following. When we cannot contract an SCC X, so when this inequality holds, when the diameter is too big for us to contract the SCC, then we grow a BFS tree from some suitable source S. I will not go into the details about how we choose S, but here in the talk, you can just think of it as being picked arbitrarily. And then you pick a suitable BFS layer, ESEP. And now, if you look at this SCC, this is our SCC X. If you remove this ESEP, these edges here, that will decompose the SCC into smaller SCCs. And if they also violate this diameter bound, then you will recursively split them as well. But let's say that the process stops here. Now you can find a DAG by contracting all the SCCs here and contracting all the SCCs here. So you get a topological order by putting these before these over here, because it's this is a one-way separator, so you cannot have any back edges here. So, but now we need to add these edges, these blue edges back in, so we don't get a topological order, we get something close to it, because the blue edges are back edges here. Now the goal is to ensure that on a shortest path pi, again with the length in this range here, this sum we had before for DAGs also holds. So this inequality we had for DAGs where we had order n here still holds in general graphs, but only in expectation. And this is actually enough that the expected value of this sum is roughly order n. So the idea is to pick ESEP in a special way. We pick this separator as a random BFS layer from an exponential distribution. And then we can show that with high probability, and I'll not give the precise statement, but roughly what we're showing is that with high probability, for every edge E in this SCC X we're looking at, the probability that that edge is a back edge is less than or equal to this fraction here. And I claim that this actually implies this bound here on this expected sum, expected value of this sum. So I'll just look at some special cases. Suppose that you look at an SSE X of size n, so the whole graph is a big SSE. Then the right-hand side of this inequality becomes this here. So this is roughly 1 over delta, which is remember, delta is roughly the length of the shortest path we're looking at. So what does that mean? That means that if you look at your shortest path pi, in expectation, you will only have roughly one edge, a logarithmic number of back edges that belong to this SSE and belong to the shortest path. And each such back edge can send you all the way from the end of the approximate topological order to the front. So how much does that contribute to the sum here? Well, for each such back edge, you can get n here to the contribution to the sum, but you only, in expectation, only have a logarithmic number of such back edges. So this bound still holds. So what if we have the case where we're looking at SSEs of size n½ let's say? Then you get the same right-hand side, except you get a factor 2 here. So now you would expect twice as many back edges on this shortest path pi that belong to SSEs of this size here. Okay, but because of the way we organize our SSEs and the way we organize our approximate topological order, each such back edge can only send you at most n½ backwards in the topological order. So this factor 2 here is dealt with by the fact that we only, each such back edge only contributes by n½ to the sum. And therefore, if you generalize this argument, you can show this bound here. And just to my final slide here. So we also need a way to detect when an SSE has too large diameter. When do we need to partition this SSE? And this amounts to detecting when a vertex of this SSE is too far away from our root of the SSE. And this is basically the problem we're trying to solve for the whole graph, because we're maintaining shortest path distances. So we're already solving essentially this problem. So the idea is to apply our data structure recursively on SSEs. But this is the most technical part of the paper. I will not have time to go into the details. So I think I'll stop here. Thank you.
Okay, thank you. So we have time for a question. Any question?
So, Christian, what is known about deterministic? I forget in this space.
So what if our structure is randomized, but there are also deterministic structures. But this,
what is best known for deterministic decremental?
So there is actually a talk coming up the next session, but you have the classical even-Sherlock structure, which is mn total update time. So that would be n cubed for dense graphs.
That's still the best?
And it has been improved now. And I think that's the next talk, basically.
Oh, okay, thank you.
Yeah.
And also there is a question on the chat, like, does it only work against oblivious adversary, and if so, why?
Yes, so we need the oblivious adversary assumption. And so the reason for that is, so actually, even if we assume the oblivious adversary, even if you have the oblivious adversary assumption, we still have the problem that our data structure itself works as an adaptive adversary if we're not careful, because we have this recursive recursion here on the last slide. I mentioned this recursive step. And so basically the way let's see how I can explain it. So the way you partition when you split the time step where you split an SSE depends on the random bits that are used for that structure. So these layers are sort of not independent of each other if you don't do this carefully. And that's why we need this. It's not just enough to assume an oblivious adversary. We actually need to work hard to make sure that the data structure doesn't work against itself as an adaptive adversary.
Yes, sure. So maybe you can continue the discussion on Slack channel. So let's thank the speaker.
Thank you.
So next talk is maybe, okay, Maxi. Can you share your slides? Okay. So the next talk is by Maximilian Proust Gutenberg. He will speak on deterministic decremental reachability, SCC, and shortest paths by directed expanders and congestion balancing.
Even that title fills the talk almost. This is trying to work with Aaron Bernstein and Tachaful, so Ranarak. And in this talk, we will address the problem of SSSP and deterministically in directed graphs. But I will go over the problem statements briefly. So we have two problems that I'm going to mention. So first, the strongly connected component problem. In the static setting, you're given a graph G, right? The one on the right-hand side, for example. And you have two vertices there. And if these two vertices are on a common cycle in that graph, then you call them strongly connected. This is just a reminder what a strongly connected component is. And the strongly connected components are just the maximal sets of vertices that are pairwise strongly connected. So you have something like this. These are the strongly connected components. And this is a very fundamental problem and well understood in static graphs, I would say. There's a linear time algorithm for it by Tarchin. But in the decremental setting, this problem is not so well understood. And in this decremental setting, essentially the graph is undergoing edge deletions, and you want to find a data structure that supports or processes these edge deletions via operation delete, which deletes an edge like this. And then you have a query operation where you can input any two vertices. So it doesn't have to be UV here, but if you would query for these particular vertices, you would know that they're still strongly connected by your data structure. And if one more edge deletion occurs that is disconnecting these SCCs, then the query should now reflect that and should actually give you a no, right? And the second problem that I'm going to talk about in this talk is the decremental approximate single source shortest path problem. This is what Christian just presented, right? So I'm gonna make this quick. Again, you have a source vertex and you want a data structure that supports your edge deletions and essentially a query operation that gives you the approximate distance from S to V in your current graph. Like here, for example, the distance changes a lot from S to V due to that edge deletion. So even for a reasonable approximation, this should be reflected in your query. All right, so I'll delve right into the results. And here I'm going to focus on a deterministic setting only to keep it clean. So there's this data structure by Evan and Chaloak, which essentially gets total update time MN for this problem, or more specifically, only for the single source reachability problem. And this is a data structure from 1981. So the single source reachability problem is like only for one vertex you can detect whether it's strongly connected to all the others or not. And here the total update time means that if you have M edge deletions over the entire sequence, then the total update time for handling the entire edge deletion is O of MN time. Queries here are constant time. And this data structure by Evan and Chaloak was then taken and kind of refined, and there's a very nice algorithm by Wonsky that gets actually the same result for SCCs, so total update time MN. But still, the fundamental problem, even for single source reachability, there's not been an improvement since the 80s. And this MN barrier is a very significant barrier for this kind of problem, of decremental problems. And in this talk, or with our paper, we actually show that you can go beyond this MN barrier. And we give an algorithm that runs in time roughly MN to the power 2/3. And I'll just point out that in the randomized setting, this is very well understood. So we have a linear time algorithm. It's just a deterministic setting where we kind of seem stuck I would say. And actually our algorithm, we also give an algorithm for the decremental SSSP problem that I just showed. And here, I mean, there's really no improvement over evidential logs data structure, which not only solves single source reachability, but also SSSP exactly in total update time MN. And this has never been improved upon, I guess, since the 80s. But in this work, we actually show that you can also break this barrier, at least for very dense graphs, and you can get total update time n to the power 2 plus 2/3, roughly, right? And again, the best result in the randomized setting was the one that Christian just presented with an n² update time algorithm. So it seems like semi-understood in the randomized setting, but again, for the deterministic setting before this work, it was really unclear how to even attack this MN barrier. All right. I'll go a bit into the technique. So I'll try to give a decremental SCC algorithm that runs in time m to the power 1 plus 2/3. This gives an improvement only in very sparse graphs, but it shows how you can use one of our main tools, directed expander decomposition, or directed expanders, to actually achieve like some result beyond MN. So the idea here is, so first, I mean, we need a notion for directed expanders. So I'm gonna take a small step back, which is going to undirected expanders. And here, essentially, an undirected expander, there you would define a sparse cut here as the first thing to like establish what an expander is. And a sparse cut is given a cut S and not S, so a bipartition of your vertex set, where S is the smaller side of the cut. You say that this cut is phi sparse if the number of edges leaving the set S is smaller than phi times the volume of S, right? So the number of edges incident to the set S. And here phi should be thought of as something very small, so 1 over square root n, for example, or 1 over polylog n, at least smaller than 1. Now in the cut that I show below, that is probably not a sparse cut, since you can see that a lot of edges are leaving this cut, so probably it's not phi sparse. And this is actually what we want. We want Phi expanders, which we say about a graph G, if we cannot find any Phi sparse cut in that graph G. So then we call it a Phi expander, which is something very desirable, right? Because it's intuitively a very, very well-connected graph. And there's this celebrated result on expanders, which is a Phi Expander decomposition that has been used a lot in the past. So in particular, you can give a vertex, find a vertex partition of a graph G, and then each of the vertex sets, if you take the induced graph with that vertex set, you have that it is a Phi expander for each I. And the edges that go between expanders are not included in any induced graph, those are few. So in particular, there's only phi m such edges. Yes. I have an example here. So here you can see some like complete subgraphs or almost complete subgraphs. So you would make those the expanders, and then you have like some edges going in between, and you can delete them out. Sorry, I don't have a slide that deletes them. And you can delete these red edges, and then you essentially get some different subgraphs that are connected and that are really well connected. Now I'll transfer this notion to the directed setting, and here the main thing is that you can now look at a cut S and not S, and you might have a lot of edges in between, but this does not mean that you can easily go from S to from not S to S or the other way around. So in particular, S might have many edges leaving, but it might not have many edges entering, for example. And this does not correspond well to our well-connectedness idea. So here we would define a directed sparse cut to be a cut S not S, and say that it's phi sparse if either it's the number of outgoing edges or the number of ingoing edges is smaller than phi times the volume of S. And once you have that, again, you can define a directed Phi expander and just say that this is a graph that has no directed Phi sparse cut. There's a notion of I'm jumping here, of a directed Phi expander decomposition that was not known so far, I think. And that is, again, you get a vertex partition x1, x2, and so on. And again, the induced subgraphs are Phi expanders. And now you again have a set R of at most phi m edges that you can remove from the graph, and then you might hope to disconnect. But instead here we're just saying that if you delete these edges, these few edges from G, and then we contract all the expanders, the remaining graph is a DAG. So in particular, the graph might be very messy and look a bit like this, but you might still find, so color coding helps here a bit. You might still find really good expanders. And now you might identify a few edges in between expanders, the red edges, and when taking them away, the edges going between the expanders after contracting them form a DAG. And this is actually the best thing we can do for directed graphs. And we think that this is still a sensible notion of an expander decomposition. Yes. I'll hurry up a bit. Sorry, that's the last slide. So once you have a directed Phi expander decomposition, it's actually quite easy because each Phi expander is definitely a strongly connected component. You just know that. So at least you know that given a Phi expander decomposition and deleting the edges in R, you know that the graph G that you have, that actually the set x1, x2, x3 is now really the set of SCCs in that graph, in the graph G minus R. And now we know that, so we can actually maintain this Phi expander decomposition in M over phi squared time, such that R is an incremental set. I'm going to copy over. Sorry, I'm rushing a bit because I'm late, I think. And then there's this helper theorem from Wonsky that essentially says that deleting a few vertices from your graph is actually fine if you can then find the SCCs in the graph G minus these vertices. So in particular, you have a vertex set S that you can remove from the graph, and if you can maintain the SCCs of G minus S, then there exists like a lifting lemma such that you can find now the the SCCs of G in time M times the number of vertices you remove. And if you combine these two and you just set phi to be 1 over M to the power 1/3, you can maintain an expander decomposition in time M to the power Mn to the power 2/3, and you will actually get a set of edges removed from that graph of order M to the power 2/3 that you just take out of the graph, right? And then you know the SCCs of that graph. And now if you put the endpoints of these edges that you took out and put these endpoints into the set S that Wonsky fixes, then you will get, again, an algorithm that lifts your SCCs from G minus S to just the SCCs in the graph G in times M 1 plus 2/3. All right. I think I'm going to stop here. I have a summary that we break the MN barrier and that there's nice techniques in this paper, but you should really ask questions at that point.
Okay, thank you. So we have time for one quick question. So Julia asked, like for SSP, there is a question on the chat. For SSP, can you return the approximate shortest paths or just the distances?
We can query the shortest path. And we can query it actually in time linear in the number of edges of the path.
Okay. Chandra, you have
I think you should refer to directed expander decomposition has been thought about before, right? And not exactly in the same way you're stating it. But I mean, I have a paper with Alina N.A. on routing, which is precisely related to it, and directed tree width is also related to it.
Oh, that's
So,
actually quite nice. I didn't know that. That's good to know. Yes.
Okay, so let's thank the speaker again. And so next talk is by Gremoj. Yeah.
Okay.
Please tell
Sure.
me.
So let me just share the slides. Okay. Nice. Can everybody see this?
Yes. So next talk is by Gremoj Goransi on fast dynamic cuts, distances, and effective resistances by vertex sparsifiers.
Okay, thanks a lot for the introduction. This is joint work with Li Chen, Monica Hensinger, Richard Peng, and Tachapon Saranurag. In previous talk, we saw what dynamic graph algorithms are, but I'm just gonna try to do this again. And it's basically you're given a graph, the graph undergoes edge insertions and deletions, and the dynamic algorithm must be able to accommodate for these changes in the graph. And at any time, you can ask a query. For example, what is the shortest path distance between you and B in graph G? And G is the current graph here. And you get an answer, and this answer can be either exact or approximate. And what you want to, what is the objective here? You want to actually design an algorithm that has a small approximation factor. And in this case, like you want to approximate some graph property like shortest path distance. And at the same time, you want to minimize the update time, which is the time to handle edge insertions and deletions, and the query time, which is the time to handle the queries. And there are several variants of dynamic algorithms studied in the literature. You have fully dynamic algorithms where you support edge insertions and deletions, decremental where you only support deletions, and incremental where you only support insertions. So what do we do in this paper? We basically try to come up with a rather general framework for designing dynamic graph algorithms. And by doing this, we attack many, I would say, challenging problems in graph-based optimization. For example, we look at max flow, also there are some shortest paths, and random walk-based simulator scores like effective resistance. And the key tool behind all these ideas is the notion of vertex sparsifiers and their generalization to data structures. And many of the algorithms we design in this paper do satisfy some of the nice properties about dynamic graphs. For example, some of them work against adaptive adversaries, and even some of them are deterministic. So let me try to tell you briefly at a very high level what a vertex sparsifier is. So the idea is as follows. You're given a very big graph G, and you have a labeling of the vertices. Some of the vertices are labeled red, some of the vertices, and the rest is labeled black. And you care a lot about the red vertices. So these red vertices are widely referred to as terminals in the literature. And the goal is to basically come up with a graph H, which is much smaller than G, and retains these terminal vertices. So it must include the terminal vertices, but can also have additional vertices in the graph. And at the same time, we must be able to preserve some graph property interests, like think of distance, like shortest path distance, think of max flow or electrical flows in the graph, only among vertices that I care about, right? And then that's where you see here that I only care about preserving this property between any pair of vertices from this terminal set, okay? And obviously the objective is to construct a sparsifier with as small approximation ratio as possible, which I denote here by alpha, and the size of the sparsifier, of course, must be also as small as possible. So this is a very powerful tool, which has been studied, I would say, extensively in approximation algorithms and not much in the dynamic setting. So we're kind of trying to bring this idea to the dynamic world. And so the key question that we ask in the paper is basically, why is vertex specification useful as a tool for designing dynamic data structure algorithms? And when you ask this kind of questions, you try to basically come up with a few requirements, what makes this kind of objects useful. And we precisely do this in the paper. So the first requirement is that we need fast algorithm for computing vertex specifiers. Ideally, we would like to be able to compute vertex specifiers in nearly linear time. The second requirement is how efficiently can we actually update a sparsifier with respect to adding terminals. So if I'm given some fixed terminals in the beginning and I compute a sparsifier, now all of a sudden I want to add the new terminal. So how efficiently can I update the vertex sparsifier so I have a sparsifier with respect to the new terminal set, T prime in this case. And the third property is that the graph property that I'm looking at, for example, flows or multi-commodity flows, shortest paths, or effective resistance, they must be actually decomposed with respect to sparsification. So if I've already constructed the sparsifier age of G, if I add a single edge to H, then the H union E must also be a sparsifier of G union E, while not losing anything in the approximation quality. So when we started looking at the problem, basically we said that, well, what's the simplest thing you can get? And it turns out that if you just look at requirements 1 and 3, then you can get offline dynamic algorithms for example, for max flow and shortest path, which are, I think, simple and natural, but also interesting because they don't use anything about dynamization. But here you also have this requirement that all updates are given to you in advance. All queries and updates are given to you in advance. So already vertex sparsification is interesting when you don't do anything in the dynamic setting. But if you want to design fully dynamic algorithms where the sequence of updates and queries is given online, and there are these updates, this update sequence and queries are not really revealed to you in advance, then we basically need something more, right? And the simplest meta theorem in the paper is that if you satisfy the requirements 1 and 2, so if you can implement them efficiently with overheads Fn and Gn in the running times, and if you can look at this, if you look at this graph property Pg and you can compute this in mhn time, then actually you can come up with efficient algorithms or efficient incremental algorithms for approximating this graph property that you're looking at. And the update and query time that you get is essentially m over b Fn plus beta Gn Hn. So this is the simplest result that you can get from our paper. And it's actually possible to extend this result if you do multi-level hierarchy. So you basically recursively build something on a sparsifier, and you can also extend it to fully dynamic graphs. But I'm not going to get into the details on how you do that. So let me tell you, the algorithm is very simple, and let me tell you how you use vertex sparsifiers here. So what we do is basically initially at the beginning of the algorithm, you just compute an alpha vertex sparsifier, and then you remember that you need to rebuild the sparsifier ever beta operation. Beta can be chosen based on the parameters you get. And now whenever you get an edge insertion, what you do is that you take this edge and you take the endpoints of this edge UV and include them as terminals. And remember, we wanted to support this addition of terminals efficiently. So I'm assuming you can do this efficiently here, like precisely with Gn overhead. And then you take these terminals and add them as terminals to the sparsifier. Once you have done this, you take the edge and add it to the sparsifier. Now you can add the edge because these terminals exist in the sparsifier, okay? Whenever you have a query, you kind of do the same. If you're looking, for example, for approximating max flow, you just take, and you are asking, well, what is the max flow between U and V? You take U and V, and then you append them as terminals to H, and then you just compute the max flow answer on H and report this as an approximate answer, right? So this is essentially the algorithm, and it's like a two-line proof to actually show that you get this running time, okay? And for more complicated versions of like doing fully dynamic meta theorems and everything else, we get the first result for approximating max flow in dynamic graphs. So our result, which is a log n approximation, but at the same time, you also get sublinear running time. And this is the first result in general graphs for max flow. And we also improve some previous work on approximating effective resistances using this technique of vertex sparsifiers. And for incremental algorithms, where I'm allowed only edge insertions, we can, for example, approximate shortest path or pair shortest path in undirected graphs with constant approximation, very large constant approximation, but also the update time is essentially very small polynomials for both inquiry time. And our algorithm is deterministic, and so it doesn't use any assumption. It doesn't use eventual trees or anything, and is entirely deterministic. It is based on Thorpe-Zwick distance oracle. So let me just tell you a bit more about the fully dynamic max flow, just an overview about this problem. So obviously this is a cornerstone problem in combinatorial optimization. Unfortunately, in the dynamic community, we haven't seen much progress in this space. I would say the only works that we've seen so far, for example, apply to Rasheshri graphs like Italiano and others, had an algorithm which achieves exact max flow, but then the running time is n 2/3, n 2/3, but this applies only to planar graphs. You can also maintain a cut specifier, for example, by the work of Abraham and others, and you can just compute the answer on a cut specifier, but this doesn't really give you a sublinear running time. And you also have a lower bound from Dalgaard, who basically proved that you cannot get a sublinear running time if you are seeking exact maintenance of max flow. So we know that our estimation is necessary, right? And again, what we achieved is a nearly logarithmic approximation and a sublinear time. And there is also a concurrent work, which I would like to mention, and Tachapol and I are involved there too, where you get dynamic max flow with very small update time, like n to the 1, but also we increase the approximation to a subpolynomial. And at the high level, our algorithm is based on maintaining dynamic J trees from Madri, and the other work is based on maintaining dynamically Rekha trees. But you can look at the long version of the talk. Unfortunately, I didn't have time to go into details about that. So to summarize, we introduced a general framework so we're trying to basically build a framework to design sublinear dynamic approximate algorithm for graph optimization problems and not look at problems specifically. And there are, of course, many open problems from our work. Like our approximation is, I would say, high right now. It's logarithmic. Can you push this down to a constant? Also, can you employ a hierarchy? For example, Madri could do this in the static setting. We don't know whether we can do this in the dynamic setting. And can you use our framework for other LP norm minimization problems? And I would like to conclude this talk with a question that I think many people want to solve, at least people who have worked on vertex falsifiers. So are there vertex falsifiers that preserve terminal cuts with arbitrarily good approximation and dependency, or polynomial dependency on the number of terminals and this approximation error? And unfortunately, I think there has been a lot of effort trying to understand this question, but we don't understand it. And it seems like vertex falsifier is a very important tool, and it's connected to other fields of algorithmic graph theory. So I would like to see more progress on this question. Thanks a lot.
Thank you very much. So we have time for one question. And
quick question on the last question. Is there a dependence on log n? I forget the best known. It's
sorry, which one?
The vertex paths for the existence question. What's the size that's known for 1 plus epsilon?
I think essentially nothing is known.
Nothing
interesting is known as far as I know. I think there are constant approximations, but then you have, I think for bounded degree graphs, I think Julia has some work on that.
I'm trying to, Julia is here, maybe she can answer.
Yes, but for 1 plus epsilon approximation and polynomial dependency on the number of terminals only, nothing is known.
I see. Thank you.
Sure.
Yes, I wasn't sure if we were talking about dynamic or
just static.
No, this is vertex. No, like in the end I talked about like this is the main question, static, right?
Yeah, for static. So there is, you can have just k terminals but log n approximation.
Yeah, exactly.
Or you can.
But also the running times there are not ideal too. For example, if you look at the work of Moitra, then he requires, I think, at least m squared running time. So even for like getting log k over log k, we don't know whether you can actually get a good running time.
Yeah. And with constant approximation, you can get something that depends on the degrees of the terminals.
Yes,
Or
so if you have bounded degree.
but nothing that is independent of that. Nothing that depends on K.
Yeah.
Wait, what is the degree dependent bound you get for like constant approx? And
So it depends. I think you can get a trade-off. So my paper has like a constant approximation and like D2 cube, but you can get like 1 perceptual approximation, and then you're gonna get D2 1 over epsilon, something like that. So you
can get D to the 1 over epsilon, but
I'm not sure what's exactly the trade-off. I don't remember it already. But it's like simple welding decomposition. There's nothing else there.
Do you hope that these constructions can be actually speed up? Because those constructions are usually require exponential time, I think.
So my construction, I see. Yeah. So my construction just does welding decomposition. Yeah, and it's true. It's if you want to get constant approximation.
So I'm sorry. Let's continue the discussion on the Slack, and Roy will please share your slides. Yeah.
Okay, give me just 1 sec. Okay, can you see this?
Yes. So the next speaker is Roy Levin. He will speak on fully dynamic submodular cover with bounded recourse.
Hey, so welcome to my talk. Today I will tell you about fully dynamic submodular cover with bounded recourse. This is joint work with Anupam Gupta, and both of us are from CMU. So I'd like to explain to you what this title means, and best to do so maybe with an example first. So suppose I give you the hitting set problem. I give you a collection of vertices and a collection of subsets of the vertices, and I'd like you to pick the smallest number of vertices to hit every subset. But actually, I'll give you a harder problem. So I don't tell you anything up front, and instead, the subsets are going to arrive and depart over time. Your goal is to always maintain a feasible and competitive solution, and you'd like to minimize the number of edits you make to your solution between rounds. Right? So perhaps this subset arrives, you pick this vertex, another subset arrives, it's already covered, so on and so forth. Maybe eventually this subset departs, and you decide, okay, I'll get rid of this, this vertex. I don't need it to stay feasible. Okay, so as I said, the goal here is to find a good trade-off between the approximation quality at every point in time and the number of edits you make to your solution between time steps. Okay, so the second quantity, the number of edits you make to your solution over time, this quantity is known as recourse. So that was the hitting set problem, but actually we're going to take a step back and zoom out and abstract the core features of the problem, all right? So there are a list of possible choices. I'll call this script n. These are the vertices we can pick from in the hitting set example. A solution consists of a subset of the choices. There is a cost associated with every candidate solution. In the hitting set example, this is just the number of vertices you've selected. There is a notion of coverage quality associated with a set of vertices. This is, in the hitting set example, the number of sets you've hit with that choice of vertices. And crucially, this notion of coverage is evolving over time, right? So how many subsets I've hit depends on which subsets are currently in the system. So this is the problem. We're solving a min-cost subset selection problem subject to the constraint that some function is maximized. Now, of course, we can't zoom out this far. If this is the problem you actually want to solve, this is hopelessly general. So we'll assume a few more things about f, and they hold in the case of hitting set. Okay, so we'll assume that f is monotone. So if a subset A is contained in a subset B, then f of B is greater than f of A. With this, we can rewrite the condition that f is maximized as f of s equals f of the entire ground set. F is non-negative, and f is so-called submodular. Okay, so it has a decreasing marginal returns property. In one slide, function f is said to be submodular if for any two subsets of the ground set A and B, A contained in B, and an element x outside of both A and B, f of A union x minus f of A is bigger than f of B union x minus f of B. So x gives more benefit marginally to A than to B. Okay, in a picture, my valuation function for cars is submodular if buying a car gives me more value if I don't already have a lot of cars. Okay, so this is the problem that we actually would like to solve. Min over of S, cost of S, subject to the constraint that f of S is maximized. And f is monotone, non-negative, submodular, and somehow evolving over time, though I have yet to say exactly what I mean by this. And we want a competitive solution over time with low recourse. So in fact, this is the fully general problem that we solve in our paper. For this talk, we can assume that f is integer valued and that all the costs are 1, but we handle the general case in the paper. So what is this problem? Offline, this is known as submodular cover. It was introduced by Woolsey in 1982. Woolsey showed that the greedy algorithm gives a log f of n plus 1 approximation. Recall n was the entire ground set. This is known to be optimal unless p is equal to np. And I'll just note that it generalizes the classic log n approximation for hitting set with n sets. All right, so let me try to convince you that submodular cover, if you haven't seen it, is extremely expressive. So version 0 of it is the hitting set problem that we've been talking about, also known as set cover. Good, so really it captures many variants of this problem. So a partial version where one need only cover some fraction of the subsets and not all of them. Capacitated variants where every vertex can be used only for some capacity number of subsets, and yeah. And Frankenstein's of these and so on and so forth. So none of these are like immediately kind of special cases of the hitting set problem, even though they look similar, but they are special cases of submodular cover. So beyond theory applications, this problem is really used in a huge number of areas in practice. And I won't harp on this too much, except to say that it's kind of become a popular paper template to take one's favorite problem, reduce it to submodular cover, and then use algorithms for submodular cover as a black box. So here's like a long list of papers that do this. And the point here is that if we can port submodular cover to a dynamic setting, we're porting any downstream application of it to a dynamic setting. And a lot of these applications do make sense in dynamic contexts. Okay, so let me just say a little bit more carefully what I mean by the function evolving over time. So we'll imagine that an adversary is going to inject and delete submodular functions to an active set. And we'd like to maintain a feasible cover for all of the functions in the active set. Okay, so a little bit more carefully. So suppose at time 1, my active set G1 consists of just the function F1. At time 2, maybe I get another function, and this goes on. Maybe at time 5, a function is deleted. So at time t, we always want a solution st for the function capital F, which is the sum of all the functions currently in the active set. Okay, and when I say S is st is a solution for F, I mean that it satisfies the submodular cover constraint, okay, for the function capital F. Now, because each of these constituent submodular functions are monotone, S being a solution for F happens if and only if S is also a solution for all of the constituent functions. Okay, so this is effectively taking the logical and of all of these constraints in the active set. Now I said we want low recourse, and formally by recourse I mean the sum over time of the size of the symmetric difference of solutions at successive time steps. Okay, so we pay 1 every time we insert something or delete something from our solution. Okay, so just to set the stage for our results, in a stock 2017 paper, Gupta, Krishnaswamy, Kumar, and Panigrahi, this is Anupam, gave a log n competitive order 1 recourse algorithm for the fully dynamic hitting set problem. So this is the special case that we've been talking about. And one should note that this is best possible. Why is that? Because log n is the best you can do even offline, and you really need order 1 recourse per time step. So if I only give you subsets that are completely disjoint from one another, then you have to pick a vertex per time step. Unfortunately, this does not easily generalize to submodular cover. Separately, so Anupam and I, earlier this year at SODA, gave an optimal algorithm for the online variant of submodular cover, where one is not allowed any takebacks. So once you buy an element from the ground set, you're forced to keep it forever. However, this really only works in an insert-only variant of this problem, and fundamentally cannot work when functions can be deleted from the system. And unfortunately, because the requirement is so stringent that you not take back any decisions, this gives a suboptimal competitive ratio in the fully dynamic setting. In other words, you can do better if you're allowed some recourse. So without further ado, here is our main theorem. we show that there is a polytime and furthermore deterministic algorithm for fully dynamic submodular cover that achieves two things. It achieves a competitive ratio of order log of capital F of n. So F, this is the sum of all the functions in the system, and n is the ground set. And this recourse bound. So I don't have time to unpack this kind of too carefully, but this is the average over time of the function, the sort of constituent function arriving at time t, evaluated at the entire ground set. So if you'd like, you can watch my my longer talk or read the paper or talk to me and unpack it more carefully. But the important thing to note is that these bounds are essentially optimal. And the reason for that is that they recover the log n in order 1 in the special case of hitting set. Now I've hidden something. I've hidden like a log term, a single log term that depends on the ratio of costs in the problem in a tilde here. But in our paper, we show actually how to remove this log for a structured class of instances of submodular cover that includes the hitting set problem, but is not quite as general as the full submodular cover. Right. So I have one slide about the algorithm. As I said, please come talk to me if you'd like to know more. The algorithm is going to do the following. It always maintains a permutation pi on the ground set. Okay, and it's maybe helpful to think of it as this picture. We imagine that this permutation pi is the history of some auxiliary algorithm. So this auxiliary algorithm picked the red element first, then the dark green one, then the yellow, and so on and so forth. And the vertical bars here denote the marginal coverage, the marginal extra like gain in the function value f of each element that the algorithm selects, given what came before it in the permutation. So given such a permutation, this automatically induces a solution to the problem at hand, which is just the prefix of this permutation where the heights of in this diagram are non-zero. And our dynamic algorithm is, what it does is it maintains such a permutation and it performs local search on the permutation itself. So it does some sort of swaps and rotations of this permutation. And the way we argue about this is we say that when the local search terminates, this permutation looks like the history of something that's very similar to a greedy algorithm. It's an approximate greedy algorithm. And for that reason, it gives a competitive solution. And furthermore, we argue that it must converge to such a history of a near greedy algorithm in a small number of updates. And this argument goes via like a potential function that's an interesting quantity called Salas entropy. So that's it. Some takeaways. So our work simplifies previous work on dynamic low recourse covering and generalizes to a significantly wider range of problems than was previously known. We introduce a new local search framework and a new potential function in the context of dynamic algorithms that I really hope find uses elsewhere. So there's a bunch of open questions. First and foremost, I'd love to remove the log term from the recourse bound that I sort of believe is an artifact of the analysis. Can one give worst case as opposed to amortized recourse bounds? So the bounds that I showed you are amortized. Can one apply this, as I mentioned, to other problems in dynamic algorithms? And finally, is there an update time variant that makes sense to consider for this problem? So with that, I'll end. Thanks, and answer any questions.
Okay, thank you. So there are like, David, can you ask your question?
Sure. Thanks for a good talk, Wade. So you said in the talk, I don't know if this is a special case you were referring to just for the talk or in general, you considered recourse unit cost recourse, right? Right. Let's say in the hitting set variant, every item you add or remove, that costs you, one unit of recourse. Mm-hmm. Can you say anything about general recourse?
So what would this look like? So different
to show it's impossible, but is there, so, some let's say in the hitting set setting, right? One of these items costs a lot, one of the vertices costs a lot more to add or remove from your solution.
Right. That's interesting. I haven't thought about it. I don't want to rule it out. There might be a simple modification to deal with it. But I would have to answer it offline because I don't know off the top of my head. I'm trying to go back to the takeaway slide, but.
Okay, and Chandra has a comment, remark. So, Chandra, you
Sorry,
want to say it or?
I don't see it.
Yes. So in the special case when the sets are small, you get better bounds. Is there some of that translates into the online setting, or that's too hard, or lower bounds exist?
So you're saying like the frequency parameterization? No.
Set size parameterization, right? So you get, if all the sets are small, you get ln D rather than, even Wolsey's result gives you ln of max of Fi.
Oh, right.
Maybe it's not.
Yeah,
possible.
so actually, so in the competitive ratio, sorry, I didn't mean to cut you off, yeah.
No, I'm wondering if there's a lower bound which precludes something nicer like that.
No, so actually our analysis just shells out to the analysis of the greedy algorithm. So essentially what we're doing is running an approximate greedy algorithm where instead of taking the actual like best possible thing, we take something that's within like alpha of the best kind of coverage to cost ratio in the costed setting. And so we get the guarantees of the greedy algorithm with an alpha fudge factor. So we do get like ln of set size.
Okay. That's
yeah.
nice. And also the second question is, you consider F to be just the linear sum of the F's. Is that, suppose I take some weighted sum, maybe that's what David's question was. I didn't quite understand.
I
Does
see.
it make even sense? Maybe I'm wrong.
So I think David's question was more about recourse. So he's saying like if something, different elements cost the different amount to add or remove to my solution. So I think that's different, but well, it should. I think the weighted sum is maximized if still like I don't think it should change anything, right? Like they're all monotones of modular functions.
You can fold it into the F itself. So yeah.
Yeah.
So, yeah. Okay, I'm confused. Okay, sorry.
Yeah. No, that's okay.
Okay, so let's take other questions offline, like on Slack channel. So let's thank Roy again. So next talk is by Tejpal, I guess. Yeah. Okay, so the last talk of this session is by Tejpal Saranurag on a deterministic algorithm for balance cut with applications to dynamic connectivity, flows, and beyond. Okay, please.
Thank you, Jugal. So this work is a joint work with Julia, U, Jason, Danupon, and Richard. And just to motivate this work a bit, why it's exciting, at least for me, let's look at the application a bit. So the first application is dynamic connectivity. This is just one basic dynamic graph problem where you are given a graph and this graph undergoes edge update, and you just want to check if the graph is connected after each update. So it has a long history, and Epstein et al. Shows how to solve this problem with just root n, worst case update time. Then there are some more development, a lot of things on amortized update time and so on. But people ask, can you really just improve this root n time, worst case update time, to something significantly less than root n and still deterministic? So this work, we did it, and it's a deterministic and quite small update time, not Las Vegas or Monte Carlo. There are more applications to other graph problem like MacFlow and so on, where there are some like slower deterministic algorithm which is known. For this problem, people can show a faster algorithm which is randomized, but they are all Monte Carlo. They can make mistake. So here we again like de-randomize all of them without like with some small loss in running time, but like it's essentially the same running time. But it turns out that the core subroutine of all of this application is based on something called balance cut or prune subroutine. So let me tell you what it is, right? What is this core subroutine? But to do that, I need to define something first. We said that the cut S is a Phi sparse cut if the number of edges that go out of S compared to the volume of S, which is basically the sum of the degree, if this ratio is less than phi. So think of phi as like something's like smaller than 1, right? So this is like the edges that go out of a cut is relatively small compared to the volume of the set. And so that is Phi sparse cut. And we said that the graph G is Phi expander if there is no Phi sparse cut. So every cut is kind of expanding. And think of expander as like 1 over n to the little 1 expander in this talk. So now this core subroutine, balance cut of Prun. So this is a subroutine that's given a graph. You need to return some cut S on the smaller side. And one of the following case must hold. The first case is that this cut is a balanced and sparse cut. So S is quite sparse, and the volume of S is like a 1/3 fraction. So it's a balanced sparse cut. On the other hand, you can return S that can be small, even empty, that's fine. Otherwise, we need that the number of edges going out of S need to be quite small. But the most important thing about this case is that the complement of S must be an expander. Like the complement of S here induce an expander, right? So it's like a variant of well-known balance cut problem, but in the case that you don't return a balanced sparse cut, you kind of guarantee that you might just remove some small set and you guarantee that the rest of the graph is an expander. So that is the subroutine. And the main theorem that implies everything basically is to show that there is the deterministic algorithm for this subroutine, which is nonlinear. And the quality here is n to the little 1. So the expander here is quite good. And I don't have time to go into here, but I just want to tell you very briefly that it really implies everything from balance bow cut prune subroutine here. Because given a graph, what you can do first is that if you have this subroutine, you just recursively apply this subroutine into the graph. If it returns a balance cut, you apply recursively on both sides. If it return, let's say here, if it return a prune case, here is an expander, you just recurse on the smaller side, the prune part, and so on. Keep doing this until all the part is guaranteed to be an expander. Combine everything here. This induces a vertex partition of a graph, and it can be shown that this is exactly something called expander decomposition, that each part induces an expander and there are few edges crossing each part. And once you get an expander decomposition deterministically and fast, you basically get everything else. You can see like in the paper, or I give a talk on this thing in this link. But okay, let's look at this. This is the main contribution. So let me tell you how to do it. So the key idea is that, okay, we observe that there is a two-way reduction between balance bow cut prune subroutine and something called cut matching game. I tell you what it is. There are two-way reduction between these two things, but this is like kind of a chicken and egg situation, because the reduction doesn't reduce the size of the instance. And so that is why the key idea in this work is to resolve this chicken and egg situation. So, okay, but let's look at this first. If I show that if we have a balance cut prune subroutine, then we can solve cut matching game. So we reduce from this to that. Cut matching game is very nice. It's a very nice framework by Kareka, Rao, and Barsirani. It's a process for building an expander from few adversarial matchings. So more specifically, it's this process. Start from, let's look at here, okay. Start from an empty graph, right? There would be like several rounds. In each round, you need to choose a bisection A and B. And then there would be some adversary that choose some perfect matching crossing this bisection. And you add this matching into the graph. And then choose the next bisection. Then the adversaries add another matching, which can be adversarial. And the goal of this game is that you need to choose this bisection cleverly so that just after a few rounds, X become an expander. So the union of this matching induce an expander. But note that this matching is adversarial, right? Okay, so it turns out that you can solve this very fast. You can find each bisection very fast, deterministically, so that after just log n rounds, you get an expander. So since this paper KRV, this is known how to do it randomized, or it can be done deterministically and slow. But what we show is that if we have this subroutine bound cut prune, the algorithm is so simple. You just run bound cut prune on the current graph, get some set, and choose A to be any set that contains this S. It turns out that the analysis is just the same, like very similar to KKOV, and but although they didn't define this bound cut prune, this definition allows us to it fit into the framework and make the algorithm so simple. So that is like one way of the reduction. And in the another way, I don't really have time to tell you how it works, but let me hand wave a bit just so that you get the flavor how it works. But the first thing that you might need to know is that let me skip this, sorry. Okay, so the reduction from bound cut prune to cut matching game is to do something called we want to embed a big expander into a graph. I don't have time to define what is embedding, but the point is that because you need to embed an expander into the graph will kind of certify that the graph have a good expansion, but to do that, you need to run cut matching game on top of this expander, on top of this graph, with is of size n. So the size of the instant is not reduced. And the key idea is that, okay, we don't want this n term. We want something smaller, n over k. So the key idea is that instead of here, we divide the graph into k parts. Try to embed k expander simultaneously into each part. And to embed this thing, although I didn't define it yet, to embed this thing, you need to solve something which is similar to like a special case of k commodity flow. But because it's a special case of this problem, we don't need a black box k commodity flow algorithm. We can use dynamic shortest path to actually solve k-commodity flow problem. But the idea is that it's really that you kind of reduce the size of this to n over k. And once you can once you can embed k expander into the graph, then you need to do something more, but it is an easy part that I will not go over it. So now once you have this reduction to solve bar cut prune, you just need to solve k many cut matching game on smaller graph. You use the first reduction that reduce cut matching game to bar cut prune again. And here you get we get a recurrent from bar cut prune to bar cut prune. And by solving this recurrent, you get like something like close to almost linear time. So that's like a flavor of how it works. So to conclude, we get this main subroutine in nearly almost linear time. And the key idea is to know that there is kind of a two-way reduction between bar cut prune and cut matching game. And we resolve a chicken and egg situation by embedding k small expander simultaneously instead of just embed one large expander. To do this simultaneously, you need to solve some k-commodity flow, but it turns out we can use dynamic shortest path algorithm to solve it. The last thing that I think might be nice to note is that we know many expander construction, which is deterministic and fast. Mathematician shows it and like this like a zigzag product. So these are how to construct expander fast and deterministic is known. But this is like when you have a full control on the graph. What cut matching is what cut matching can give you is that you can construct an expander even if there is some adversary in the framework. And what we show is that we can construct this deterministic and fast. I just think it's just a nice perspective how to construct expander. The last slide, the open problem is we have this interliteral one. Can we improve it to polylog? The one simple problem that capture all of this is this problem. Like, it's a good special case that I think is interesting. Is that you just need to distinguish two cases: whether the graph has no sparse cut at all, like it's a very good expander, or it has like 1 over log to the 100 sparse cut. So quite like a very sparse cut, but not polynomially sparse, like 1 over polylog sparse. Can we distinguish this in m polylog time deterministically? If you can do it, that would be great. Yeah. Thank you.
Okay, thank you, Tejpal. So we have time for one quick question. So Amir asked, like, what is the running time for a smaller phi, such as 1 over square root n?
So in the paper, we show how to do it in near linear time, almost linear time as well. So m to the 1 plus little 1, even when phi is very small. But you need kind of another step I didn't talk about it in this talk.
Okay, thank you. Okay, so let's thank all the speakers.